I'm Dr. Regis J. Sirinko, founder of iMathTutor, a private university-level mathematics and statistics tutoring service. We provide face-to-face tutoring for Penn State University Park students and online tutoring for graduate students and professionals around the world. We'd like to welcome you to this, our first screencast. We hope it to be the first of many. I'd like you to think about a procedure that can be carried out repeatedly. Tossing a coin is a good example of such a procedure. A stopping rule for the process of repeating the procedure is an instruction to stop the process whenever the procedure produces some particular result. In the case of tossing a coin repeatedly, you could toss until, say, the first head is observed. The number of times the procedure repeats under the stopping rule is called the stopping time. If the outcome of the procedure is random, then the stopping time is a random variable. Hence, one may ask, what is the expected stopping time? It is well known that the stopping time until the first head is observed in repeated tosses of a coin is a geometric random variable. Consequently, if the coin is fair, the expected stopping time is 2. In a recent number file video, 2 other stopping rules for a fair coin flip process are discussed. A small physical simulation is carried out in the video to estimate the expected stopping times for these stopping rules, and the actual expected stopping times are given without proof. Determining the expected stopping times for the 2 number file stopping rules is an advanced undergraduate level probability problem, such as one that might be found in Sheldon Ross's book, A First Course in Probability. So although the problem itself involves some pretty detailed argument, which is what makes it an upper level problem, the actual probability theory that we use may be found in, say, an introductory lower level course in probability. So you may be able to understand this lecture if you've had some probability, not necessarily at the upper level, undergraduate level. We've decided to make this a topic of our first screencast because the solution nicely illustrates the use of conditioning arguments. The number file video which inspired us is by Dr. James Grime and is entitled Consecutive Coin Flips. You can find it at the link, although I would suggest going to YouTube, searching for number file, and then trying to find the consecutive coin flip video. It's probably a lot easier than trying to remember that link. So let's review. The model of recorded coin flips is a sequence of IID, or independent identically distributed Bernoulli random variables, x1, x2, so on and so forth, where xi equals 1 if the outcome of the ith toss is a head, and xi equals 0 if the outcome of the ith toss is a tail. Further, the probability of head is equal to p, whereas the probability of a tail would be 1 minus p. Here p is some number between 0 and 1. Now, let's consider the situation where we repeatedly toss a coin until the first head is observed. Well, you go through this as a simple example to help us fix some ideas that we'll be using in the later on in this screencast. So here are a few sequences which stop when the first head is observed. The stopping time for this process, i.e. the number of tosses required to observe the first head, will denote by y, and for the 3 sequences we see here, y is 5, 3, and 6, respectively. The standard conditioning argument will now be used to find the expected stopping time, E of y. We're using, again, a well-known result from probability theory. That is, the expected value of y is the expected value of the conditional expectation of y given x1. Clearly, if x1 equals 1, that is, if we get a head then on the first toss, then y equals 1. Consequently, the expected value of y given x1 equals 1. On the other hand, if you get a tail, x1 equals 0, and since the flips are independent, the process resets after the first toss. So the number of tosses after the first that it takes to observe another head has the same distribution as y. It follows that the conditional expectation of y, given x1 equals 0, is 1 plus the expected value of y. So, summarizing what we found so far, the expected value of y given x1 equals 1 and the expected value of y given x1 equals 0 equals 1 plus the expected value of y. Now, let's compute the expected value of y using this well-known result from probability theory. We have that the expected value of the expected value of y given 1 is the expected value of y given x1 equals 1 times the probability that x1 equals 1 plus the expected value of y given x1 equals 0 times the probability that x1 equals 0. Making our substitutions for both the conditional expectations and these probabilities, we arrive at the expression that the expected value of y equals p plus the quantity 1 plus the expected value of y times the quantity 1 minus p. We can solve this expression for the expected value of y. And we do that if p does not equal 0, we get that the expected value of y equals 1 over p. Now let's move on to the stopping rules from the number file video. In the first one, a fair coin is tossed repeatedly until 2 consecutive heads are observed. Here are a few examples of sequences of coin tosses which result in 2 heads stopping the process. Let t denote the expected stopping time of this process. That is the number of tosses which have occurred when the process stops. For these 3 processes, you have t equal 10, 5, and 8, respectively. The second experiment that was considered in the number file video is a fair coin is tossed repeatedly until a head is immediately followed by a tail. For this stopping rule, we have a few sequences of coin tosses and would stop when you get a head followed by a tail. We'll let S denote the stopping time of this process, and the values for these 3 sequences are 6, 4, and 7, respectively. The experiments are very similar, yet the expected stopping times, expected value of t, and the expected value of S are not the same. The standard conditioning argument will again be used to show that the expected value of t is 6 and the expected value of S is 4. The coin flips are modeled as, again, we've already noted this earlier. This is just here to remind you. The only difference in our current situation is that we're using a fair coin. So the probability of a head equals the probability of a tail equals 1/2. Now, if x1 equals 0, for both of the experiments to stop, the penultimate for the process to stop, the penultimate outcome must be a head. Therefore, if the first toss is a tail, then the process will not stop on the second toss for either stopping rule, regardless of the outcome on the second toss. This means that since the tosses are independent, that if the first toss is a tail, the process resets after that toss. Put another way, the number of tosses required to stop after the first toss, if that toss is a tail, has the same distribution as the stopping time before the first toss. Consequently, the expected value of t given x1 equals 0 equals 1 plus the expected value of t, and the expected value of s given x1 equals 0 is 1 plus the expected value of s. We list so again, we list what we've just shown. Now let's move on to the situation when the first toss is ahead. In this case, it's possible for the process to stop on the second toss for both stopping rules. Therefore, it becomes necessary to condition on the outcome of the second toss. For stopping rule 1, the process stops if x1 equals 1 and x2 equals 1. For stopping rule 2, the process stops if x1 equals 1 and x2 equals 0. Clearly, the expected value of t given x1 equals 1 and x2 equals 1 is 2, while the expected value of s given x2 equals 0 and x1 equals 1 is 2, since the process stops after the second toss. So here we have a summary of what we've just found. Now, in the case of the first stopping rule, if the second toss is a tail, then it cannot be the penultimate toss, because the penultimate toss must be ahead. Thus, whenever x1 equals 1 and x2 equals 0, the process resets just as it did when the first toss was a tail. In the case of the second stopping rule, if the first toss is ahead and the second toss is ahead, the process may or may not stop at the third toss. In this case, the process resets, but really only partially. That is, if the second toss is ahead, the number of additional tosses after the first toss, before the process stops, has the same distribution as the number of tosses given that the first toss is ahead. Therefore, the expected value of t given x2 equals 0 and x1 equals 1 is 2 plus the expected value of t, while the expected value of s, given that x1 equals 2, x2 equals 1 and x1 equals 1, is 1 plus the expected value of s, given x1 equals 1. Again, summarizing what we found so far, we want to use these results now to find the expected value of t given x1 equals 1 and the expected value of s given x1 equals 1. For the first stopping rule, again, we use this well-known result from probability theory, and note that the inner expectation here is a conditional expectation, and so is the outer. So these probabilities must be conditioned on x1 equals 1. However, we have independence, so we can drop those conditions and make substitutions from above to obtain the fourth equation on the right. This simplifies, and we therefore have that the expected value of t given x1 equals 1 is 2 plus a half times the expected value of t. For the second stopping rule, again, we use this well-known result from probability theory, and again, use the definition of expectation, and having to use a conditional probability, which reduces to an ordinary probability because of independence. We can then substitute from the above expressions and substitute for the probabilities, and we arrive at the expected value of s given x1 equals 1 is 3. So here we have, again, a summary of the results so far. Finally, these conditional expectations are used to find the expected value of t and s. Again, going back to our trusty result from probability theory, the conditional expectation of t is the expected value of the conditional expectation of t given x1. Using the definition of expectation, we arrive at the second equation on the right, and then substituting, that becomes 3/2 plus 3/4 the expected value of t. This is solved for the expected value of t. Hence, the expected value of t is 6. Returning to our result from probability theory, the expected value of S is the expected value of the conditional expectation of S given x1. The expected value of S given x1 equals 0. So now we just use the definition of expectation and make substitutions to find that the expected value of S is 2 plus 1/2 the expected value of S. This is solved for the expected value of S, and we end up with the expected value of S is equal to 4. So in summary, we find that if a fair coin is flipped repeatedly until 2 consecutive heads are observed, then the expected stopping time of the process is the expected value of t equals 6. And if a fair coin is flipped repeatedly until a head is immediately followed by a tail, then the expected stopping time of the process is the expected value of S equals 4. In part 2 of this video, we're going to look at conditional expectations a little bit closer. So, what we're going to do is use analytic arguments to show that, to derive these various expressions for the conditional expectations. The first step is, well, we can, again, we have here for your reference the model of a repeated coin flip. And the first step is to express the stopping times t and s as a function of the Bernoulli random variables that model the process. The functions which are used are modified versions of the function which relates a geometric random variable y to the underlying Bernoulli random variables. This well-known function is presented as motivation for what follows. Now, consider the random set of natural numbers, n, such that the sum on I equals 1 to n x sub I equals 1. The smallest value in this set gives the number of tosses needed to observe the first head. Hence, y is the minimum value of the set n such that that sum equals 1. So we're going to keep some things up here at the top for your reference as we go through, remembering that we're dealing with an IID sequence of Bernoulli random variables, and that the geometric random variable can be expressed in terms of these Bernoulli random variables as written there. It would be useful to introduce two new dependent sequences of Bernoulli random variables. So for I equals 2, 3, 4, we're going to set u sub I equal to x sub I minus 1 times x sub I, and v sub I to be x sub I minus 1 times 1 minus x sub I. So notice that if the ith and ith minus first tosses are both heads, u sub I is equal to 1. If either of those tosses are a tail, then u sub I equals 0. On the other hand, if the ith toss is a tail, x sub I equals 0, so that 1 minus x sub I is 1, and x sub I, if the ith minus first toss is a head, would be 1. So v sub I equals 1 if the ith minus first toss is a head and the ith toss is a tail. It would be 0 otherwise. So in summary, we know that u sub y equals 1 if and only if both the ith minus first and the ith toss result in heads, and v sub I equals 1 if and only if the I minus first and I toss result in a head followed by a tail. The new sequences are used to define two sets of random numbers, just as we did for the geometric. So what we have again is that the stopping times are given in terms of these sets as the minimum n. So mimicking what we did in the case of the geometric. We'll keep these up here for your reference. Consider the random variable t given x1 equals 0 and s given x1 equals 0. If x1 equals 0, then u2 equals 0 and v2 equals 0. The other u's and v's are independent of that event that x1 equals 0. x1 does not figure in the definition of u3, u4, v, and so on and so forth, v3, v4. So notice now that those random sets, simply all that differs between A given x1 equals 0 and the set A is that in this set, the summation starts at 3. Likewise, for B given x1 equals 0, the summation begins at 3. We're going to now define ui prime to be ui plus 1 and vi prime to be vi plus 1 and n prime to be equal to n minus 1. What this will allow us to do is shift these indexes back to 2 here. So the beginning of the summation will now be at 2. And so now with this, we have the following expressions for A given x1 equals 0 and B given x1 equals 0. So I want you to notice here that our summation now starts at 2. So it looks very much like what we have here and here. So now the conditional stopping times are going to be given by taking the minimum over those random sets. And this will be our defining equation. So this minimum is t prime, that minimum is s prime. Now, notice that here we're summing random variables, the same number of random variables, and the ui primes and the ui's have the same distributions, so these sums have the same distributions. Likewise for the vi's and the vi primes, so those sums also have the same distribution. It follows that t prime and t and s prime and s have the same distributions. Hence, the expected value of t prime equals the expected value of t, and the expected value of s prime equals the expected value of s. It follows that the expected value of t given x1 equals 0 is 1 plus the expected value of t, and the expected value of s given x1 equals 0 is 1 plus the expected value of s. Next, we're going to turn attention to t given x2 equals 1 and x1 equals 1, and s given x2 equals 0 and x1 equals 1. Given that x1 equals 1 and x2 equals 1, u1 equals 1 with probability 1, and given that x2 equals 0 and x1 equals 1, v2 equals 1 with probability 1. These are the situations here where you have the first two tosses are ahead, and here you have the situation where the first toss is ahead and the second is a tail. It follows that t given x2 equals 1 and x1 equals 1 is 2, and s given x2 equals 0 and x1 equals 1 equals 2, both with probability 1, and consequently we have that these conditional expectations are both equal to 2. Next up is t given x2 equals 0 and x1 equals 1. This corresponds to the first toss being a head and the second one being a tail. Given that x2 equals 0 and x1 equals 1, u2 and u3 are both equal to 0. Notice that x2 is going to enter into the definition of both u2 and u3. Here it appears for u2 it is the second factor, and for u3 it's the first factor. In either case it equals 0. Further, that the random variables ui, I greater than or equal to 4, are independent of the event x2 equals 0 and x1 equals 1. This is because for I equals 4, neither of these random for these random variables, neither x1 or x2 enter into their definition. So now our set A, conditioned on the first toss being a head and the second is a tail, is equal to this. So notice all we've done is now starting our summation at 4 because the first two terms are 0. And again, defining new random variables and n prime so that we can start to sum at 2. It follows that we can write this conditional random variable as 2 plus t prime, where it will should come as no surprise that t prime has the same distribution as t. Consequently, we have that the expected value of t, given the first toss is a head and the second is a tail, is 2 times the expected value of t. Finally, x2 equals 1. So we're going to look at the situation where the conditional expectation of s, given the first two tosses are heads. We first consider the case of s given that the first toss is a head. In this case, v2 given x1 equals 1 is 1 minus x2. If you come up here, plugging 1 in for the first factor, we get 1, and so we only get the second factor for v2 under these conditions. So we'll set v2 prime equal to 1 minus x2, and for I greater than or equal to 3, vi prime is going to equal vi. Then we get that the conditional, this set B conditioned on the first toss being a head, can be written in a similar fashion to what we've already written for up here, starting our sum at 2. Hence, s given x1 equals 1 equals the minimum of this set. Now, we'll come back to this in a second. We want to now move on to v2 given x1 equals 1 and x1. So v2 given the first two tosses are heads. Obviously, 1 minus x2 would be 0 in this case. So this v2 conditioned on this is 0 with probability 1. v3 is going to be v2 times 1 minus, I'm sorry, v3 is going to be x2 times 1 minus x3. So since x2 is 1, v3 conditioned on this event is just 1 minus x3. And so we'll set v2 prime equal 1 minus x3 and vi prime equal I plus 1. I equals, and n prime equals n minus 1. With this set B conditioned on the first two tosses being heads can be written as we have it here. Hence, s given the first two tosses are head can be written as 1 plus this conditional random variable. Now notice this sum and this sum will have the same distribution. So when n prime equals n, so we have that the conditional distribution of s prime given x1 prime equals 1 has the same distribution as s given x1 equals 1. It follows that the conditional expectation of s given x2 equals 1 and x1 equals 1 plus the expected value of s given x1 equals 1. So, as promised, we've given analytic arguments to derive these expressions. This brings us to some exercises. In exercise 1, we ask you to find the expectation of S and T for a coin with probability P of landing heads. It's a very minor modification of what we've already done. In exercise 2, we ask you to find the variance of T and the variance of S for a fair coin. Here we have to use another result from probability theory, which states that for any two random variables, jointly distributed random variables, Z and W, the variance of Z equals the variance of the conditional expectation of Z given W plus the expected value of the conditional variance of Z given W. So this is going to be a little bit more work, but I think that you should be able to adapt the arguments that we've used to this situation. Our third exercise is to look at two different stopping rules. Suppose that a fair coin is tossed until two consecutive heads are observed, R times. Let T of R denote the stopping time for this process. We ask you to find the expected value of T of R. In the second, part B is, suppose that a fair coin is tossed until a head is followed by a tail is observed R times. Let S sub R denote the stopping time for this process, and we ask you to find the expected stopping time for this process. Now let's look at a couple of sequences in A to fix ourselves as to exactly what's going on. So when R equals 2, notice that the process can stop here because we have two consecutive heads, we have a tail, and then two more consecutive heads, so it stops. We've had two consecutive heads 2 times. Here we have a sequence of tail, head, tail, tail, followed by head, head. So we have two consecutive heads once, but the second head then combines with the third head to give you consecutive heads a second time. So it stops here. For B, it's more straightforward. When we're stopping for a head followed by a tail 2 times, here we have 2 tails, head, tail, then a couple of tails, head, tail. The process stops here. Here we have tail, head, tail, a couple of tails, a head, another tail. So the process stops here. In both of these sequences, we've had a head followed by a tail 2 times. Our hint is to adapt the method for computing the expectation of a negative binomial random variable from the expectation of a geometric random variable, each with the same probability of success. And now a word from our sponsor. Remember, we offer face-to-face tutoring for Penn State students and online tutoring for graduate students and professionals worldwide. Visit our website to learn more about iMathTutor and to arrange a free consultation. You can also email or call us at help@imathtutor.org or call us at 814-317-6284. Thanks for watching, and check back here for more videos in the upcoming weeks.